So yes, we've listed four types of decay, and as well we've listed some. We've gone through three types of bombardment reactions. Let's just see what they would look like. Okay, so let's start with alpha decay. We'll do beta and gamma. Let's go for it. So here's the first one. We'll start with our alpha decay, right? So part one is for radioactive guys. Let's do, and we'll do a alpha decay. Alpha decay, what would it look like? We want to do an example. We want to see a situation where we would be dealing with an emission of an alpha particle. What would we have? So here's an example. Let's say we have radium, which is, now we are looking at the things we've talked about, those that the nuclide notation, okay? Let's see our nuclide notation. It'll be 226, then 88, and this would be radium. Now, because this is an atom, we know what the top number is. This is mass number, right? And we know what the bottom number is. The bottom number is obviously the atomic number, right? This is our atomic number. So maybe let me just use the notations. This is mass number A. This is atomic number Z. Now, what we know is you may look in the periodic table and see this radium, this Ra, having a different is a value from 2 to 6, okay? Because this 2 to 6 is the mass number. It is not the atomic mass. Though sometimes the mass number and atomic mass are exactly the same, but they may be different. So we never use the periodic table to get this value, okay? We only may use the periodic table to get this one, then the atomic number, because we know for radium, the atomic number is never going to change. It's just going to be the same. So we'll go to radium and see it. Now, let's say that this is a reaction, right? So we put our equal sign. This is the equal sign for these chemical reactions. Let's say now we get 222 and 82. And this is radon. This, and 86 rather. And this is now radon. What would we then have? Would then put our alpha particle, which is 42 helium. This is the alpha particle, like a helium nucleus. And we have put our equation. We may put it, instead of helium, we may put an alpha particle, although we most of the times would write He. So this is our alpha decay, and that's how we would write it. Now, how would we know? So when we write these equations, we use the rule that we use when we are balancing reactions. And that rule says that the sum of protons and neutrons for the reactants is equal to the sum of protons the sum of the protons and neutrons is equal of the reactants is equal to the sum of protons and neutrons of products. And the sum of the protons alone is equal to the sum of the products. So we can say that the total A, which is the mass number of the reactants, is equal to total Z, right? Is equal to total A of products, rather. So we are dealing with reactants and we are producing products. So what we say is this. We like to write it like this. We like to put our products here, like to write it like this. Then we say the total A of reactants is equal to the total A of products. And then the total Z of reactants is equal to the total Z is equal to the total Z of products. Remember that A is your mass number, right? So the mass number for reactants should be equal to the mass number of protons. And then the charge or atomic number of the reactants should be equal to the charge or atomic number of products. So we'll add the top numbers. So here we'll say this is 226. For here it'll be 222 and 4, which leads to 226. Then here we have again 88. Then here we have 86 and 2, which go to 88. So this is how we can see that the numbers on the left are exactly the same as the numbers on the right. The reactants, the top values are the same as the top values of the products. This would be our alpha decay. Make sense? All right. Now we go to the next one, which is going to be our beta decay. Okay. So we can have it as our beta decay. Now we have beta plus and beta minus, right? So first we'll go through beta minus. Let's start with beta minus. Beta decay, you'll say beta minus. What would we have? Now, what you should know is, what is this beta minus particle? What is it? We said it is like an electron. It's functionally equivalent to an electron. Then you say to me, an electron coming from the nucleus? How is that possible? The nucleus does not have electrons. Where is it coming from? Well, here's where it comes from. What we have is one of the neutrons that will be inside. This is very important when you now see the example of an equation. One of the neutrons inside your nucleus will split into a proton and an electron. That electron is what we call a beta minus particle. It's an electron that moves at a high speed. So it's a fast moving electron that is emitted from an unstable nucleus. So we have an unstable nucleus. Then what will happen is one of the protons will burst, change to a proton. And as it changes to a proton, it will shoot out a fast moving electron, very fast moving electron. And this is what we call a beta minus particle. Okay, so when we show it, we show our neutron 1, 0 going to be 1, 1 p plus 0 minus 1 electron. Okay, or 0 minus 1 beta, but we like to use electron. This is where it comes from. And then when we write it in an example of then a reaction of something that does that, let's say we have carbon, so we'd say 14,6 carbon. Now this is an atom. Carbon is an atom, so we know the top is the number of protons, then the bottom is going to be our number of protons only. This is the mass number, this is the atomic number. So here we would have our mass number. Remember, if you go in the periodic table, you will not see carbon having 14. You may not see it. In this case, we already know it's not going to be 14. But where do we get the 14 from? This is an isotope. This is the mass of a certain isotope of carbon. One of the carbon guys. So here we will have an atomic number. Okay. So isotope is like the different races of mankind. So here when we say we have an isotope, it's the same, it's a human being, but then we have different varieties. So here an isotope is one of them. So it's just one of the varieties, like to say Asians or whatever. Sorry for this. This could be a little bit personal, but I'm just giving it as an example. Nothing, no hidden intention. So here, this is a carbon, and it can go to become a nitrogen atom. Then what happens in this process? It can then emit your beta minus particle. So what happens here, if you see, we had 6 protons. Now what will we have? 7 protons. Do you know why? Because we said a neutron is going to convert to become a proton. The top number is not going to change because the sum of protons and neutrons will remain the same because we've changed a neutron to be a proton. So the top number, the sum of them both will still be the same. But what we know is the bottom number, we now have more protons. Then what's going to happen? We should shoot out this beta minus out here. We know that since this is now a nuclear particle, we say that this number is now charged. For these beta guys, it is charged. It is not atomic number anymore. So here's an example. Now we go to see where we are now going to deal with a positron or a beta plus. Positron is going to be your beta plus. We saw our beta minus the electron. So now let's see what we would have. We first question would say to me, where does a positron come from? Well, a positron is the reverse of what made an electron. A positron now comes from a proton converting itself to be a neutron. So what we first have is we start by having a proton, which then goes to become a neutron. And when it does that, it's going to shoot out the energy in the form of somebody called a positron, which is 01e. And we say it is a positron is an antiparticle of an electron. Antiparticle means that it has the same mass but opposite charge. So it has the same mass as an electron, but now it has the opposite charge. Electron has a charge of 1. This one we have a of -1. This we have a charge of 1. Remember, this is just the charge. It is not the atomic number anymore, because this here we are dealing with nuclear particles. Be sure you remember that. Now, here, what would we have as an example of something like that happening in a reaction? So we have this guy that is very funny. He's called technetium. And that we can write it like this to say 9543 technetium. This can go to become 9542. So the number of protons will reduce, but the top number will remain the same because we have a proton converting itself to become a neutron. But what do we know? When it's like this, we know that a positron is going to be released. What will be a positron? The top will be 0, the bottom would be 1, and then you can put E for electron. Okay, now we can have the sum of the numbers on the left being equal to the sum of the numbers on the right. Now we go to the fourth one. D is electron capture. Okay, the fourth one, electron capture. Then we talk about gamma emission to be done. So electron capture, what happens? Well, this happens when you have the decay of something that is unstable, a nucleus that is unstable. Okay, now how does this nucleus that is unstable decay? It is going to get an electron and capture an electron or pick it up. All right, and what happens when it picks it up? What happens when it picks it up? What it does is it goes into the inner shell, one of the inner shells, and it's going to the inner shell, right? It's going to take an electron from there. Okay, when it takes an electron from there, then you're going to have it decay. All right, and what happens is when we get the product, we will have what? We will have the atomic number go down. Because what happens in electron capture is when we are now writing the equation, electron will now go on the left-hand side. So here's an example of an electron capture. But what we can first show is what would happen here. We would have a proton, right? And this proton would go ahead and give us this. What will it give us? It will give us a positron plus a neutron, right? Plus a neutron. Now, what then happens is this reaction that we have just shown here, this can now be done in reverse, where I would take this electron to that other side. I would now have 1p, getting 0 minus 1 electron, a proper electron. So my positron has gone to the other side of the equal sign. Its sign will change to be minus 1. And this would give me a neutron. This is still true. So that is what we are doing in electron capture. What will be having? Something like potassium. So we can say potassium is K, right? And what would happen is we'd put our numbers 40, then 19. This is potassium. Don't be surprised if you go in the periodic table and don't see these numbers. We've said that this top number is the mass number. It's not the relative atomic mass. So what happens is it now meets an electron, 0 minus 1. That is electron capture, E. And then what's going to happen is it's going to have 40 plus 0 is 40. Here 19 minus 1 is 18. And anything with 18 is argon, AR. So this is what happens in electron capture. Okay, we have something that is excited, something that is unstable. Okay, the unstable nucleus will, what should I say? It will capture an electron, and when it captures an electron, it is going to be converted into a more stable state. Now, the last one is going to be this called gamma. So let's talk about it, and we would have it. So this would be our gamma emission. Now, gamma, remember, it's a ray, and it's like this. This is the symbol. So what happens with gamma is this. Gamma, remember that it is 0, 0. It's just a ray. Then we don't have any nuclear notation. But what gamma does is, after the alpha decay and beta decay have happened, alpha decay or beta decay have happened, the atom we get might still have too much energy. We say it can be in the excited state. An excited state means you have more energy than what you must have, okay, in that state. So when it's in an excited state, it will then lose more energy, okay, through gamma emission. And then now it will become stable. Okay? That's what happens. Does it make sense? That is, after an alpha decay or a beta decay, We may need to throw away more energy to then become stable. And we can only do that by throwing a gamma particle. Okay? So now let's show an example. You would have something like this. 99, 43. We've thought about this technetium, right? And then what they show you is they'll put an M. M means metastable state, which means it is excited. Right? Then what's going to happen to it? Well, this is what happens. We would have it form 9943 again. Now, what happens is if it's 9943, it is still TC technetium, right? But now this M is now gone, this for excited state, and then what would then have is 00 gamma. And this is what we need. This is for gamma radiation. Okay? And that's it for radioactivity. We'll do the next part in the next video. Bye for now.